Hello, everyone. My name's Ethan. Over here is Scotto, and we got Taylor over in the other screen. This is our heat transfer project proposal. And you want to hit the next slide, Taylor? All right. We are doing a flamethrower. Yay! The one we chose specifically was the XL18. It's offered by a company called Flame. It is the most powerful commercially available flamethrower in the United States. It's kind of an interesting device, and it differs a little bit from the conventional mid-20th century flamethrowers used in things like World War II or Korea. Instead of using the pressure of the gas inside of the container to throw the gas and then ignite it on the way, it uses a bit of a Venturi effect with a CO2 canister, and then you just put like diesel or whatever in the tank unpressurized, and it's a lot cheaper to operate that way. Also, instead of like a arc starter or something, it just has a little butane torch running the whole time. So it's just a lot more simple to operate than legacy designs. Want to hit the next slide, Taylor? All right. So as I kind of just went over, usually some sort of arc system would be using a flamethrower where two electrical contacts go across, and it starts what's called a flame holder. So it's just this little device that keeps a little fire going as the gas passes over it and ignites the outer layers that are contacting the atmosphere. Typically, all the gas would be pressurized, and it would be the pressure of the gas or the fuel that would propel it out. But in this one, it uses a CO2 tank that's highly pressurized, and then just normal gas, like liquid gas, such as diesel or gasoline or a combination of fuel oils and such. And that's the system that the XL18 uses. And then it also uses a pilot torch, which is like instead of just holding a flame, it has its own fuel source, so it keeps it consistently going flame. And then that pilot torch has a piezoelectric lighter, which is just creates a little spark for itself. So altogether, we chose the system because it's a kind of a new approach to flamethrowers. It's the most commercially available, and it's a lot cheaper to operate than other things. So next slide, please, Taylor. All right, now I'm going to hand it off to Scotto.
So the certain applications you can use this flamethrower for would be, potentially pest control. It's depending on the individuals. Some people, there's videos out there where people use it for ant piles or on concrete buildings. Sometimes there's like hornets' nests. You see people torch them off. It's perfect in the agricultural context for if you have, let's say you weren't able to harvest a field, you can do like a controlled burn through the fire stations. Some people use these flamethrowers to do farmland clearing, and it's more prone in sugar cane in foreign countries where they grow sugar. And that's actually how instead of plowing under the fields, they use controlled burns in order to burn all the excess product off the fields after it's been harvested. And like I was saying, you can do controlled burns, whether this is for, let's say you did a brush pile, you did some sort of brush clearing. You could use this flamethrower in order to ignite the brush piles instead of like using diesel where you just dump 5 gallons onto a brush pile. You can just use the XL18 flamethrower. And then another application you can use it in would be like de-icing. You could potentially de-ice your driveways or melt snow if you had some sort of issues with snow in certain areas. Kind of whatever context you can think about using the flamethrower, and you can go ahead and do so. And I'll let this go back to Taylor.
So the XL18 flamethrower really is comprised of 3 different modes, and actually it uses the three main modes of heat transfer: conduction, convection, and radiation. But it uses them all in different ways. The first and second mode are both conduction. So the first time you encounter conduction is just on the fuel tank, as conduction transfers heat through the fuel tank as the heat moves from the hotter areas, either combustion to the cooler parts of the tank, without actually moving itself. It's just happening through the fuel itself. And then we have another instance of conduction as the fluid meets the flame. So conduction, it transfers the heat from the flame to the fuel upon the contact of the two. It ignites the fuel by raising the temperature to combustion level at the molecular level. And then for the third and fourth instance of heat transfer modes, we have convection radiation. So the convection occurs just momentarily as the fluid transfers energy from the ignition flame to the ignition to the larger torch flame. Essentially, the convection transfers heat from the flamethrower's hot gases and fuel to the surrounding air, with the rising hot gases creating a larger torch flame. And then finally, there's radiation being emitted, not actually radiation, but radiation heat transfer that's emitted from the torch flame. Once it's kind of coming out of the actual torch, the end of the tip, and it starts to spread, radiation transfers heat through infrared waves emitted by the flame, allowing for the energy to reach nearby objects in the environment. And now we're going to pass it back to Scotto.
So for the conclusion slide, the XL18 flamethrower demonstrates the effective application of heat transfer principles through, as stated from Taylor earlier, conduction, convection, and radiation. Conduction in the fuel tanks and at the point of ignition ensures a continuous flame. Convection drives the movement of hot gases, extending the flame beyond the nozzle for greater reach. Radiation disperses heat into the surroundings, contributing to its overall thermal impact. Although the flamethrower's design efficiently transfers heat to its target, energy loss due to radiation and the dispersion of flaming fuel can limit its effectiveness. And on the right-hand side, this beautiful drawing, which was created from the TAYLOUR BEIGH, is shown, and he can go into detail on that image.
Yeah, so sorry, my bad. So this diagram essentially shows you where you're going to be encountering the different modes of heat. So we have our first instance happening on the tank, happening on the outside of the tank, because you have the hotter air on the outside, and then essentially it would be the cooler fluid on the inside, holding the fluid of the gas, I guess. And then we have our second and third and fourth instance happening up here in the actual gun. And it kind of gives you a little blown up example of kind of how you can see this is happening and transpiring. So
this is our presentation, and thanks for watching and listening.
Goodbye.
thank you. Bye.